What if a whisper from another galaxy could rattle Earth's planetary defenses? On October 1st, 2025, something 2.5 million light-years away seemingly touched our planet's invisible armor, triggering a scramble inside NASA. This wasn't a solar storm we could predict. It was something entirely new, linking the distant Andromeda galaxy to the radiation belts that shield us all. We're going to break down the signal, the response, and what it means when the cosmos reaches out in unexpected ways. Let's explore this together.
The October 1st discovery.
It all started with a routine alert that was anything but. High above our heads, a vast field of radiation called the Van Allen belts protects us. On October 1st, 2025, NOAA's Space Weather Prediction Center issued a G2 geomagnetic storm watch, a moderate alert corresponding to a KP index of 6, nothing unusual. But then, Mission Control at Goddard Space Flight Center noticed strange chatter. Automated queries to the legacy data from the Van Allen probes mission, which orbited up to 30,000 kilometers high, began spiking. The mission, operated by the Johns Hopkins Applied Physics Laboratory from 2012 to 2019, had its archives pinged hundreds of times in an hour, a clear emergency pattern. As noted by experts like Dr. Daniel Baker, a leading figure in radiation belt physics, this wasn't routine analysis. The automated pull focused on data from the Relativistic Electron-Proton Telescope, or REEPT, suggesting a specific and urgent concern about high-energy particles. These algorithms were specifically looking for anomalous acceleration gradients that didn't fit known solar wind coupling models. This high-level digital scramble indicated that the system had flagged a change in the belts that was not only significant but also fundamentally strange in its origin.
The anomalous signal.
Here's what started the entire chain of events. At 3:47 UTC, the Deep Space Network nodes in Goldstone, California and Canberra, Australia, logged a strange radio transient. It lasted only 8 seconds and came directly from the Andromeda sector, a tiny patch of sky less than a degree across. Instantly, it stood out. The signature didn't match any known pulsars or the behavior of catalogued quasars. For a normal solar radio burst, the pattern was all wrong. The signal's intensity, while faint at a flux density of only a few Jonskis, was coherent enough to be unmistakable. But the most compelling clue was its frequency. The burst peaked at 408 MHz. That's a softer, lower frequency than most fast radio bursts, or FRBs, which typically hit between 600 and 1,400 MHz. This detail is critical because lower frequencies like this are known to be in the range that can efficiently interact with and stir up electron motion within Earth's magnetosphere, a process governed by plasma physics. This wasn't just random noise from deep space, it was a signal with a frequency that, theoretically, was perfectly tuned to get a reaction from our planet's protective shields. It was a whisper, but it was a whisper at exactly the right pitch to be heard.
The belt response.
Here's where the timeline gets bizarre. Exactly 16 minutes after that strange radio signal vanished, Earth's shield flinched. 16 minutes, not instant, not hours later. NOAA's GOES-18 satellite in a geostationary orbit 35,786 kilometers high, detected a sharp, alarming uptick in high-energy electron counts from its SEISS instrument, specifically in the greater than 2 MeV energy channel. These are the killer electrons that can cause deep, dielectric charging, building up static inside a satellite's components until it discharges, frying the electronics. The outer Van Allen belt had twitched violently. Flux readings jumped by 40% in under 3 minutes from a baseline of roughly 10 to the 4th to 1.4 times 10 to the 4th particles per square centimeter per second. While a major solar storm can cause increases of 1,000% or more, this event's rate of change was unprecedented for non-storm conditions. This was confirmed by Los Alamos sensors and a brief 5 to 10 nanotesla fluctuation on ground magnetometers in Tromsø, Norway. A tiny tremor compared to Earth's 65,000 nanotesla polar field, but unmistakable. Something had nudged the belts with surgical precision.
NASA's response protocol.
When Earth's radiation belts move that fast and, the sun isn't the obvious culprit, NASA doesn't guess, it executes a playbook. The first call goes to the Space Weather Coordination Center. Step 2 is to pull real-time solar wind data from the DSCOVR satellite, which sits 1 million miles from Earth at the L1 Lagrange point. Its Faraday cup instrument showed solar wind speeds were a pretty placid 385 kilometers per second, with the interplanetary magnetic field's BZ component hovering near zero, no southward tilt that would open a door for solar energy. Step 3 involves comparing magnetometer readings from a global network, from Alaska to Antarctica. On October 1st, none of these standard checks provided an answer. The DST index, a measure of geomagnetic storm strength, was a negligible -8 nanoteslas. With no earthly or solar explanation, the situation was escalated to level 2. This means waking up principal investigators, running predictive models on supercomputers, and immediately checking the position of astronauts on the International Space Station and high-value satellites. The scramble isn't chaos, it's a methodical checklist running against a terrifying new variable, leaving forecasters with data they just couldn't explain.
The physics mystery.
This is where the real head-scratching begins, because the data breaks our models in 3 specific ways. First, the 16-minute lag. A direct electromagnetic hit should have been instant. The delay suggests a cascade. Maybe the radio burst triggered a slower-moving, ultra-low frequency wave in the magnetosphere, which travels at only a few hundred kilometers per second. Over the vast 100,000 kilometer scale of the outer belt, this travel time fits the 16-minute window perfectly. Second, the 408 MHz frequency. It's suspiciously close to bands that plasma physicists like Dr. Richard Thorne of UCLA know can stir up electrons through wave-particle interaction. His research focuses on natural Whistler mode chorus waves in the few kilohertz range. It's plausible the 408 MHz signal created a beat frequency that fell directly into this highly resonant band. Third, the signature. Data hinted at sharp changes in pitch angle, concentrated around an L shell of 4.5, a key region in the outer belt. This is the precise signature of resonant pitch angle scattering, where electrons are nudged into the loss cone and dumped into the atmosphere.
Historical surprises.
To understand the shock of this event, you have to know that the Van Allen belts have a history of, well, shattering our assumptions. In September 2012, NASA's Van Allen probes discovered something thought to be impossible. A third temporary radiation belt materialized between the 2 known belts, located at an L shell of about 3.5. It lasted for 4 weeks before a solar shock wave erased it. The lead investigator, Daniel Baker from the University of Colorado's Laboratory for Atmospheric and Space Physics, stated plainly that our models were wrong. Then in 2014, the same probes found what scientists now call the impenetrable barrier. At an L shell of 2.8, or about 11,000 kilometers altitude, the most energetic, ultra-relativistic electrons with energies above 5 mega-electron volts simply stop, unable to move closer to Earth. And as recently as May 2024, the SIR-B-C CubeSat mission confirmed the formation of 2 temporary extra rings, which persisted for months. For over 60 years, we've studied these belts, yet they repeatedly prove we don't have the complete picture. They can reconfigure in ways we can't predict, responding to forces we are still struggling to identify.
The resonance mechanism.
So, how could a faint, distant signal possibly affect a planetary system? Well, think about pushing a child on a swing. You don't need immense strength, you need resonance. The Van Allen belts are a resonance system. The 408 MHz burst was like a perfectly timed push. The energy, though weak, may have generated a harmonic that fell into the kilohertz range of natural plasma waves, like the chorus waves studied by Dr. Richard Thorne. These waves, which sound like birds chirping when converted to audio, are incredibly efficient at accelerating electrons. A 100 keV electron can be boosted to over 1 MeV in just a couple of hours inside a strong chorus event. The Andromeda signal didn't need to be a sledgehammer, it just needed to be the right tuning fork. It likely acted as a catalyst, not the source of the energy itself. It unlocked the potential energy already stored in the magnetosphere, triggering a release, much like a tiny spark, can ignite a huge explosion. This is a known process called a substorm, but it has never been seen triggered by a non-solar external pulse.
Real-world consequences.
A twitch in the Van Allen belts isn't just an academic curiosity, it has immediate real-world consequences. GPS satellites orbit at 20,200 kilometers, right in the heart of the outer belt. A sudden 40% spike in electron density can degrade the standard positioning service from 3-meter accuracy to over 10 meters, affecting everything from air traffic control to financial systems. Communication satellites can experience temporary outages, causing dropped calls and buffering streams. For astronauts, especially on future Artemis missions, an unexpected radiation spike is a serious health risk, potentially adding several millisieverts of dosage with little warning. In a worst-case scenario, intense radiation can cause permanent satellite damage, as was demonstrated by the early failure of Telstar 1 in 1962 after being exposed to a man-made radiation belt. The systems our modern world is built on are fragile, and they all run under the influence of these unpredictable belts. This event serves as a stark reminder of that vulnerability.
Testing the hypothesis.
So, how do we prove this wasn't a coincidence? You follow a strict scientific playbook. Step 1 is timestamp alignment with sub-millisecond precision across multiple observatories. Step 2 is spectral analysis of future bursts to see if they again match known resonance bands. Step 3 is global confirmation from instruments like the Themis satellites, which provide multi-point measurements within the magnetosphere. The most critical test, Step 4, is repetition. To reach the 5 sigma level of certainty required to announce a discovery, a 1 in 3.5 million chance of being a random fluke, this exact chain of events must be observed again. As astrophysicist Avi Loeb often stresses, null results are just as important. Telescopes like Canada's CHIME, an FRB finding machine, will now be cross-referencing their detections with real-time space weather data. If another Andromeda burst is detected with no corresponding belt response, that data is crucial for constraining the theory. Science advances by disproving ideas just as much as by proving them.
Background science explained.
Let's quickly break down the core science. The Van Allen belts, discovered in 1958 by James Van Allen, are two primary donut-shaped zones of charged particles. The inner belt, between 1,000 and 6,000 kilometers altitude, is mostly stable. High-energy, protons, in the 10 to 50 MeV range. The outer belt, from 13,000 to 60,000 kilometers, is a dynamic zone of electrons. The primary driver of change is the sun. Solar flares and coronal mass ejections blast particles toward Earth, causing the belts to swell. Inside the magnetosphere, a constant dance of wave-particle interactions is happening. Waves with names like chorus and hiss are always accelerating and scattering these trapped electrons. Deep space signals are also arriving constantly. Fast radio bursts are millisecond flashes from distant galaxies. Pulsars are spinning neutron stars that emit regular beams with millisecond timing precision. The October 1st event suggests a new type of interaction, where a specific radio signal from deep space might be coupling with the natural wave physics already happening in our own backyard, a concept previously confined to theory. We are left with a profound and unsettling mystery. The facts are on the table. A radio burst from the Andromeda sector was observed, and 16 minutes later, Earth's radiation belts responded in a way our models could not explain. The correlation is documented, the physics is plausible, but the interpretation remains open. Was this a 1 in a billion cosmic coincidence, or have we discovered a new coupling mechanism between our planet and the distant universe? The only way to find out is to keep watching, to test the hypothesis with rigorous, repeatable science. This is how true discovery works, not with hype, but with data. Don't forget to like, subscribe, and hit the bell icon. Thank you for watching Stellar Tech.